All right, welcome back. We're going to be going over the second part of waves today. This time we're going to be talking about the electromagnetic waves, but let's once again look at the standards that we're going to be addressing. This is 8.PS4, and this is waves and their applications in technologies for information transfer. You're going to develop and use models to represent the basic properties of waves, including frequency, amplitude, wavelength, and speed. And we talked about those in part one, and there will be a subsequent video that breaks it down just to that particular standard. Also, we're going to compare and contrast mechanical waves and electromagnetic waves. So you learned about the mechanical waves in the last section, and then we're going to be learning about the electromagnetic waves in this section. We're going to do that based on refraction, reflection, transmission, absorption, and their behavior through a vacuum or various media. And so we'll be talking about that. And then finally, evaluate the role that waves play in different communication systems. And that's going to be in our section 3. Hopefully we'll get it on this particular. All right, before we get started, I do want to talk to you a little bit about the electromagnetic spectrum, and that's what you see here on the screen. I'm going to be referring to this several times, and I'll pull it back up several times, but this should look familiar to you. We drew this on the board, you've drawn it on paper, and like I say, this is for review, so hopefully you guys have this well in your mind, but we will be referring to this several times throughout this video. Okay, we're going to be talking about electromagnetic waves today, and we need to keep in mind that these are transverse waves. These are not longitudinal, they're transverse, and that's going to involve the transfer of electric and magnetic energy. So if you think about electricity and magnetism, if you put those two words together, you come up with electromagnet or electromagnetic. And so uh, I want you to keep in mind that these always work together and they work at right angles to one another. So if electricity is traveling on a plane horizontally, then the magnetic field is going to be perpendicular to that, and it would be horizontal to that. And so I want you to keep in mind that electricity and magnetism work together a lot. But these are made of vibrating electric and magnetic fields that move through space or some medium at the speed of light. The movement of charged particles creates an electric field, which creates a magnetic field, and vice versa. These two fields generate each other repeatedly. The two fields move at right angles to each other, and these waves do not require a medium to travel. This is why they can travel through space, which is a vacuum. So we'll be talking about radiation, and we know that radiation is when energy is transferred through empty space, and that's the reason we feel the heat of the sun, and that's why we can see the sun. The light waves travel to us through empty space, and so we'll be talking about that as well. Okay, as I said, electromagnetic radiation is energy that the electromagnetic waves transfer. So we know that it's electricity and magnetism together, traveling through space, carrying energy, so that's radiation. Okay, there are two models of electromagnetic wave behavior, and the first one is the wave model of light. And this is, once again, the transverse waves. This is only when light passes through a polarizing filter does it have the properties of a wave. Ordinary light is made of waves that vibrate in all directions. That's why we can see things. If I'm looking at a blue wall from one direction, it still looks like a blue wall from a different direction because this light travels out in all directions. But a polarizing filter would allow only some of the waves to pass through that, and this light that passes through is called polarized light. I think some of you may have some polarized sunglasses. I know that a lot of people, like to wear them. They give a lot more clarity. I think some fishermen use them. They can see kind of down a little deeper into the water, and so hopefully they can find, maybe see that fish that is eluding them, and hopefully they can catch it. All right, this starts section 2. This is about the electromagnetic spectrum, and that's really the focus of this entire PowerPoint for the most part. I want you to really have that deep seated in your brain, so that you really understand it. But this is the complete range of electromagnetic waves in order of increasing frequency. All electromagnetic waves travel at the same speed in a vacuum, but they have different wavelengths and different frequencies. The first one that we come to is the radio wave. And we know that these have the longest wavelengths and the lowest frequencies. And these are used in broadcasting. I think a lot of you listen to the radio, and they have an AM and an FM. And so that's how we hear those sounds, being transmitted through radio waves. But like I say, these are the lowest energy waves on the electromagnetic spectrum, and they have very long wavelengths and low frequencies. And I want you to really keep in mind that wavelength and frequency always works opposite of one another. If it's a long wavelength, then obviously it's not going to pass a point as quickly as one that has a very short wavelength. Okay, the next section is microwaves. They're the next step up. These are what we use for cell phones. A lot of times use those because they have a little shorter wavelength than the radio waves and a little higher frequency. But these are used obviously in a microwave, cell phones, and radar. So that's the radio detection and ranging. Hopefully you haven't been in a car that's been pulled over for speeding, but they've used radar a lot of times to check your speed, but they're using microwaves in order to do that. The next level up, as we work our way up the spectrum, is infrared rays. These are electromagnetic waves, which are a little bit shorter than microwaves and a little bit higher frequency and energy than the microwave. Their energy is often felt as heat. The warmer objects give off more infrared rays than cooler objects. And so thermograms are images that show regions of different temperatures and different colors. And I think there are some creatures, that could probably see more infrared. They can sense the heat coming off of something. Even though we visibly can't see that with the naked eye, we can look at things with an infrared light and be able to pick that up. Once again, this is a good time to go back and address the chart that we were looking at earlier. Obviously, if you can see right here, we have the radio waves. They have a very long wavelength in comparison to these on the far end. And so their frequency is going to be less than as it moves along. So we're going to start with the AM radio, FM radio, and then we're going to come up into the microwave section. And that's going to have, like I say, a little bit shorter wavelength and a little higher frequency. And then the infrared. These are the three that we have talked about first. And then we're going to come to our visible spectrum. And I think a lot of you have heard the term Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. And so if you can remember that, you'll know then that the red is going to have a little less energy than the violet will. Remember, as we move from left to right on this scale, the energy is going to increase. And so a violet light is going to have more energy and a higher frequency than the red light. Any kind of red that you happen to see, that's actually at a very, relatively speaking, it's got a longer wavelength and a lower frequency than the violet. Okay, we know then that the visible light are the electromagnetic waves that you can see. These have shorter wavelengths and higher frequencies than infrared rays. Each time we're moving up this scale, it's going to say the same thing about it being a little shorter wavelength and a little higher frequency than the previous level. But this is the colors of the rainbow, and these are able to bend or refract, and that's why we have the rainbow. Next, we're going into a little higher energy, and if you remember from the uh, the visible light section, the violet was on the higher energy side, and so right beside it is going to be the ultraviolet rays. On the opposing end, where red was, the lower energy, right beside it was the infrared. So that's kind of a good way to keep them together. If you were going to go out and into the sun, you're going to put on some type of skin protection, from the sun, from the UV protection, the ultraviolet protection. You don't have to have infrared protection. So we would know then that the ultraviolet rays are a little higher energy and they're a little more damaging, and that's something you really want to be careful. When you're out in the sun. Hopefully you're getting out a lot, but do protect your skin. I'm not going to bore you by reading this, but you do understand, once again, the relationship of the wavelengths and the frequency. As we move along, each of these particular type of rays are going to have a higher frequency. These can damage skin cells, but they do help us produce vitamin D. Sometimes when you go out in the sun, some of that is good for you because it does help your body, build those strong bones. The next level up, as we get more and more energy, are x-rays. Any of you that's had an x-ray before, you know that the technician will put on some type of a coat, or they'll stand behind a wall, probably lead lined, to protect themselves from the x-rays. Unfortunately, when I was young, a lot of the dentists would do x-rays and they didn't really understand the harmful effects of those. And a lot of the dentists, from when I was younger, um, they ended up with some type of cancer from that. So we always want to be careful with where x-rays are concerned. But this has a little higher energy, and therefore it can penetrate most matter. That's why you can get an x-ray of a bone down inside of your body. And a lot of times if you've had someone that has broken a bone, I know that Quinn just had an accident on her birthday where she has had a problem with that, and so I'm sure she had an x-ray. And so um, x-rays are higher energy. They're the next to the highest level, and they do have a very short wavelength and a high frequency. But they're not the highest. The highest is yet to come. And those are the gamma rays. These are the ones that turn the Incredible Hulk into, uh, or David Banner into the Incredible Hulk. He had an overload of gamma radiation. But these have the shortest wavelength and the highest frequencies. So these you definitely would not want to be exposed to. These can penetrate almost all matter, but doctors can use them in controlled circumstances or with specific machines to see the internal organs. Gamma rays are also emitted by the stars that explode, but luckily for us, they are blocked by our atmosphere. So let's go back and look one more time as a quick review of the electromagnetic spectrum. All right, once again, notice the long wavelength. That's the distance from one point of a wave to a corresponding spot on another wave. So that's going to be a lot longer with the radio waves than the gamma rays on the far end of the spectrum. Notice the frequency is going to be a lot lower. And if you remember from the first video, the frequency is how many waves pass a particular point in a given amount of time. And so you see that the gamma rays there's going to be more waves pass a particular spot um, in a given amount of time. So we start with radio waves. The microwaves are not in here, but they should be. They go right in between radio waves and infrared. Infrared is going to be right beside the red on the visible spectrum. That's the first color that we can see. And then that goes red, orange, yellow, green, blue, indigo, violet, Roy, GBIV. Violet's going to be beside ultraviolet, which gets into the harmful section of the electromagnetic spectrum. X-rays have more energy. They can be more damaging to us. So those have a higher frequency and shorter wavelengths. And then the highest energy rays on the electromagnetic spectrum are the gamma rays. So it would be a good time to just, pause this, look away, get a sheet of paper, and then see if you can write down these levels and then even put in the visible spectrum. That's the part that our eyes are capable of picking up. Um, our eyes are an organ that is able to see this part of the electromagnetic spectrum. Okay, and then finally, we're going to put this to use. And if you remember from our third standard, it was talking about communication and how the electromagnetic waves are used for communication. And so in broadcasting, there are charged particles that are vibrating inside a transmission antenna to produce the radio waves. Anyone who has ever been out running around one of these big antennas, you can sometimes hear them hum. And these antennas are sending out waves in many directions. So obviously, uh, from that particular spot where the antenna is, it sends it out in all directions. This information is carried to a receiving antenna and converted into an electrical signal. And this signal is the sound that you hear. The same way that that works, there are also different radio frequencies assigned for different uses to prevent interference. Anyone who is related to a person in law enforcement or drives an ambulance, for example, those emergency channels are going to have their very own frequency assigned to them. Hopefully, there's not going to be a lot of bleed over on that. And so that's for official use. And then you have the radio stations. A lot of you have your favorites. I know a lot of people, I think they like 102 or 103.5 or 102.1. I'm sure you have your favorites, 107.7, but these are all different radio frequencies. And like I say, they're all set aside for different uses. There are two types of radio. There's AM and FM, and I don't know that many of you listen to the AM section anymore, but that is called amplitude modulation. That's what AM stands for. And frequency modulation is the FM. So that'd be a good thing to ask your parents, hey, do you know what AM stands for or what FM stands for? Modulation means that you're just changing it to a certain degree. You're just varying a little bit. And so the amplitude of the wave will change on the AM section, but the frequency is going to stay the same. So like I said, the amplitude's going up, but the frequency of the wave is the same. And these are long wavelengths, and they're very low energy. These waves actually have such a low energy they cannot penetrate our atmosphere, and so they will bounce off of the atmosphere. And that's why these AM radio waves can be picked up a long way away. They can travel long distances. They don't have a lot of clarity to them. But like I say, they are trapped by the ionosphere, and they can broadcast over long distances. Frequency modulation is going to have a little higher energy. They got a higher frequency than the AM does, but the frequency of the wave will change, but the amplitude stays the same. So right there, the amplitude is the level of the crest is going to stay the same on these, but it's going to occur a little quicker. It's going to have a little higher frequency. These won't travel as far because they pass through the ionosphere. They're not reflected back down. And but we do have a better sound quality with the higher energy. And then cell phones. All of us have one nowadays. But this is used, we use the electromagnetic spectrum for this. Once again, we talked about microwaves um, being the medium, being the ray that is used in order to make the cell phones work. And so when a call is placed, it sends out the microwave from your phone. Then a tower is going to pick that up and transmit it to a central hub. This hub is then going to send it to a tower. It may be the same tower. And then it's going to be sent to your phone. And this happened so fast. I believe in class we tried this. We had one person calling another, and it was almost instantaneous that the that the call went through. And so that's how fast these waves travel. So there was a lot of work being done in a short amount of time, going from a tower to a hub to a tower back to your phone. So that was very, very quick. But you do need to know that cell phones work with microwaves and that they go to a tower, these cell phone towers. A lot of times when you drop a call, a lot of us have had that happen. Um, we, it's just because, you've got out of range of the tower and it's not being able to send a signal there. And then also there's satellite communication, and a lot of us use our GPS. We're trying to find out where someone lives, and we're looking on our phone. And this is because there are 24 satellites that are broadcasting radio signals to the Earth, and it can tell your exact location on Earth or in the air. There are 4 satellites needed to pinpoint your location. Once again, as we talked about, like for earthquakes, you needed 3 different positions. So yes, you can find out where you are on the Earth with 3, but that 4th satellite actually tells how far you are above Earth's surface. And this is the end of the section about electromagnetic waves being transferred, but we have one more section with light that we want to talk about. Okay, many of us watch TV, and we have a satellite um, that is sending the TV signals to us, especially during this time. But these signals are being sent to satellites, which relay them around the world. And these signals are often scrambled, and we wonder, well, why can I get this station or I can't get the other one? And so you have to have a subscription, and then they will decode that box for you. Sometimes you may have a cable box that is unscrambling that particular signal so that the satellite companies can make money. Dish Network, DirecTV, different ones of those use that satellite communication, and you will have a decoding box in your house, and that's how that is unscrambled. Okay, this concludes the second section, the part 2, and you will be revisiting some of these as I go over the specific standard. I'll break them down a little bit further, but hopefully this has served as a good review for you, and hopefully you're staying safe and staying well. And like I always say, these are a lot easier to do when you're in front of me and I can interact with you, and I'm sure it's the same for you as well. But we make the best of a bad situation right here. But anyway, I miss you, I love you, and y'all just hang in there.